I see Alex Valenkin, director of the Institute of Cosmology at Tufts University. Alex is known for the quantum creation of the universe and eternal inflation. We last talked in 2007. What does he now think in 2014? Alex, when I first heard about multiple universes several decades ago, it was wild speculation, but just electrifying. Today, multiple universes are the standard model. You've been a key player in making this happen. Walk me through this history and where we are today.
By multiple universes, you could possibly mean different things. One way of thinking about what the universe is all we can observe, and that's rather limited, because light had time to get us from the Big Bang only from a limited region of space. And of course, if you call that universe, then we are pretty sure that beyond that, other regions similar to that exist. So in this sense, it is pretty uncontroversial to say that there are multiple universes. However, the theory of inflation brought with it a new concept of multiple universes. The idea of inflation is that there is this period of extremely rapid expansion in the early history of the universe. And when you work out this theory, you find that inflation, which ended in our region of space, creating this stuff that we see with galaxies, stars, and so forth, did not end everywhere at once. There are other outside kind of big bubble that we inhabit. There is still inflation continuing and forming new and new bubbles all the time. And the space between these bubbles is expanding very fast, making room for new bubbles to form. And these bubbles expand at speed approaching the speed of light, so we cannot possibly travel to other bubbles. For all practical purposes, each of these inflationary bubbles is a separate, self-contained universe. And they can, in principle, have different physical properties.
So what you're saying is that with the inflation that you believe is necessary in this universe, by virtue of its characteristics, must be happening again and again.
Must may be a little stronger word that I would use, but if you try to avoid this, you kind of mutilate the theory. So it's the natural consequence of inflation is the existence of this multiverse in this sense.
And so as you look at this vast ensemble of universes, can you begin to characterize them? Obviously, one is like ours.
So, in principle, it is conceivable that all bubbles have similar physical properties to ours. This would not contradict anything that we know. But a wide variety of particle physics models that have been proposed, like supergravity theories, grand unified theories, string theory, they generally predict apart in addition to our low-energy physics. By low energy, I mean the energies that are accessible to us here. Apart from our kind of environment, there can exist a number, and sometimes an astonishingly large number, for some of the theories, of different, what physicists call vacua. The property of inflation is that it will explore the whole landscape of these vacua. So whatever particle physics provides, in the course of inflation, regions with all these properties that are allowed by particle physics are going to be formed. So it will explore the entire landscape of the fundamental theory. And the space between these bubbles is expanding very fast, making room for new bubbles to form. And these bubbles expand at speed approaching the speed of light, so we cannot possibly travel to other bubbles. For all practical purposes, each of these inflationary bubbles is a separate, self-contained universe. And they can, in principle, have different physical properties.
Why is that? Why can you say that inflation explores the landscape? Why not just explore the particular one that we have now? Because that's the data point that we know.
Well, it is because the transitions between these different vacua occur through quantum tunneling. So we are located in some minimum of the energy of this landscape. And there are other minima, and quantum mechanics allows you to tunnel through energy barriers to other minima. Moreover, quantum mechanics tells us that if the transition between these two minima is not absolutely forbidden by some conservation law, then it is inevitably happening. So basically the answer is that quantum mechanics tells us that all possible transitions will happen between all the possible states. Well, that depends.
Alex contends that because the same process that best explains the Big Bang origin of our universe, cosmic inflation, does not end everywhere at once, inflation continues to generate other Big Bang universes.
Well, I just
Alex
answered the
won't
question.
quite say inflation must generate other universes. Rather, a multiverse is the natural consequence of inflation. What are some other pieces of evidence? Because there are multiple ways that seem to confirm the existence of it.
Well, the other argument that I rely on is the simple fact that there's a lot of evidence for inflation, and almost all versions of inflation lead automatically to eternal inflation, inflation that once it starts never ends. And this eternal inflation goes on, producing what in this context we usually call pocket universes, but we would be living in one of these pocket universes.
So that's in a sense a two-step process to the multiverse. One is that you need inflation in this universe to explain how this universe works. And then when you have inflation, when you look at inflation, you say, whoops,
Right.
once I get this thing
Once
started.
you've got it, it's hard to stop.
Yeah, right,
Exactly.
right.
So even though we can't see these other universes, we can say that the same theories that give us the best explanation we have of the properties of our visible universe predicts that it's going to go on forever, producing an infinite number of pocket universes.
All we need to start inflation is a tiny seed of a peculiar material called false vacuum. False vacuum has the astonishing property that it self-replicates, and it does so very rapidly. If you start with 1 cubic inch of this material, very soon you will have 8, then 64, and so on. A proton-sized seed of false vacuum could inflate to be many trillions of times larger than the entire observable universe in way less time than it takes light to travel across an atomic nucleus. While the false vacuum expands exponentially, something else happens. Microscopic bubbles emerge and start to grow. Imagine a huge pot of boiling water. Bubbles of water vapor form at random times and random places. This is very similar to how bubble universes form, except instead of water, they form in the inflating false vacuum background. Each newborn bubble will inflate for a while until an energy transfer generates a fireball like the Big Bang. Our Big Bang happened in our universe 14 billion years ago, while other bubbles will have their own Big Bang event, some of which could be taking place at this very moment. After bubbles form, they expand, but the false vacuum background expands even faster, continuously creating room for more and more bubbles to form. Thus, once inflation starts, it can sustain the production of bubble universes forever. This is called eternal inflation. The eternally inflating universe is a very diverse place, eternally inflating multiverse, excuse me. Our fundamental theories of physics suggest that there are lots of different types of bubble universes, and the mechanism of eternal inflation will see to it that all of them actually get produced somewhere in space. Distinct bubble types will have different effective laws of physics with different particles and forces. Some bubbles may even have more than 3 spatial dimensions.
Horses are unique in that they can sleep standing up. Their kneecap is held in place by 3 ligaments. During normal flexion and extension of the hind limb, the patella slides up and down in the trochlear groove. But when resting, the horse can lock its patella over the medial trochlear ridge, preventing flexion of the limb. The quadriceps muscle lifts the patella and locks it into place. Once the stifle is locked, the soft tissue structures of the reciprocal apparatus prevent flexion of the entire hind limb. Young horses experiencing growth spurts, or horses that have lost conditioning due to stall rest, can sometimes have inadvertent locking of their stifle, even when in motion. This first horse is 9 months old and was found in the pasture, unable to walk as his left hind limb had locked. This next mare is 3 years old and was on stall rest for a hoof injury. As she lost muscle tone, her patellas started locking. While this condition appears dramatic, it is non-painful. Light exercise, hill work, and trotting over cavaletti to strengthen the quadriceps muscles often resolves the problem.
Minimum, I don't have a, who has a, is this it? No, that's a pen. All right, a penultimate, that means next to last. The next to last minimum, where eventually you jump to the side of a potential, slide down a hill. In this minimum over here, we have eternal inflation, bubble nucleation, slide down a soft, slow ramp. That's called slow roll inflation, and eventually wind up with ordinary cosmology in here. All of standard model cosmology began someplace along this slow ramp here, and the rest of it is, as I said, standard model cosmology. All post-standard model cosmology is everything that happened before, including this very, very complicated landscape. The question is how to test it. And by test it, I mean more or less direct test observational tests, how to test this idea. And that's what I'm going to talk about, the phenomenology of it. I have not a lot to say about it. Unfortunately, one is very, very limited. The problem is exactly the same as the problem in particle physics testing post-standard model. The better the standard model works, the harder it is to test the post-standard model. Maybe we should call this the pre-standard model, come to think of it. This happened before, not after. But there's a prejudice that I want to dispel before I start. The prejudice dates back to exactly when, I don't know, but it's the idea that if there is inflation, there must have been a huge number of e-foldings. There must have been a huge expansion factor, perhaps as big as 10 to the 1,000. I've heard the number 10 to the million, and I've even heard the number 10 to the 10 to the million as the expansion factor of the universe during the ordinary inflationary period. I strongly believe that this is very unjustified and is quite possibly wrong. It basically came from mixing up the two kinds of potential, there are two kinds of inflation the eternal inflation and the slow roll inflation, which I think we have every reason to think are two separate phenomena, or maybe two, very likely two separate phenomena. We have to distinguish them, and when we distinguish them, possibilities for phenomenologically studying post or pre-standard model inflation begin to arise. Now, we'll have to be lucky, but let me discuss them anyway. The question is how much ordinary inflation did take place. Did it obliterate all evidence of an earlier epoch? Can we look back to when the universe may have nucleated from another point on the landscape? And if so, what will we see? And finally, I don't know if I have time to talk about it. I will, even if I do, it will be very brief. Can we see into other bubbles? Can we see into other types of environments? Of course, we can try to see them by looking into the past. We can also try to see them by looking to the side, so to speak. Okay, quick cosmology lesson. There are three kinds of cosmologies. You all know them. I won't go into them in any detail. The only thing I want you to know is that I will use, where is it? I will use the notation R, capital R, for a radial coordinate. And the rest of it you don't need to know, other than to say that there are three kinds of standard, absolutely standard cosmologies: closed FRW, flat FRW, and negative curved FRW. Negative curved has always been a bit of an orphan. Nobody's ever been quite as serious about it as the other two cosmologies. And of course, inflation tends to flatten everything, and so there's a prejudice in the favor of very, very flat cosmology. The best fit, the data is inconclusive on this, and it will never be, well, it may become conclusive, but in any case, the best fit is that the curvature is ever so slightly negative, but definitely zero is well within the error bars, slightly shifted to the negative. That one shouldn't take that seriously, obviously, but it may be that in the relatively near future, we will pin down the error bars on that much better. The anomalous behavior of low L primordial fluctuations may be another hint. Of course, it may just be an artifact and of no special interest. And I'll come to that. I'll come to what that means. But the question is, what does theory say? In particular, what does theory say about which of the three cosmologies is the right cosmology? And the theory, as I said, that needs to be tested is the theory of tunneling on a landscape. And the theory of tunneling on a landscape has a very, very definite thing to say. This is a picture, a sort of artist, I'm not much of an artist, but a picture of an eternally inflating universe giving rise and giving birth to other bubbles. The bubbles give rise to bubbles. I'm going to assume you all roughly know this picture. It has both a series and a parallel aspect to it. A given observer passes through a series of different vacuums. On the other hand, at the same time, there are parallel things going on corresponding to distant bubbles nucleated. And we can call the various vacuums ancestor vacuums, the ones which preceded our own, a remote ancestor, an ancestor, and here we are up here someplace. So that's the picture that, as I said, needs to be tested. Now, what goes on in the final vacuum, our vacuum, so to speak? Well, our vacuum, according to this picture, is a negative curved FRW universe. This goes back to the work of Coleman and DeLucia, who studied these kinds of bubble nucleations. And it's kind of odd when you think about it. An infinite negative curved universe embedded in what could be a perfectly finite de Sitter space. But of course, this de Sitter space, this is a Penrose diagram or a conformal diagram. The de Sitter space has a divergent metric up near the end of time. And so when you look at the spatial slices in here, they actually diverge at the corners here. And the preferred, as I said, geometry that would, not just preferred, required geometry that would occur from bubble nucleation would be negative curved FRW. So that's first of all, a first lesson. Now, here are the equations for a negatively curved, or for that matter, this is actually for negative curvature. This is the negative curvature term over here. This is the basic FRW equations. Everybody's familiar with them. This phi might be the inflaton. Here's the kinetic energy of the inflaton, never particularly important in anything I'll have to say. Here's the curvature term, negative curvature. That's the plus sign here. And of course, here's the potential, the inflaton potential, which may look something like that. It's not important whether this is, for the moment, a single field, multiple field, or whatever, just a tunneling from one point to a neighboring point. Here's where the eternal inflation took place, the ancestor vacuum over here. You tunnel out onto the side of this potential and slide down by slow roll inflation. During the initial phase of this, before you actually enter slow roll inflation, when you first tunnel out onto the side of the potential here, you're dominated completely by the curvature term. 1 over a squared is much bigger than anything else. And that leads to the solution of the FRW equations, which is the scale factor growing like time. That means an enormous amount of cosmic friction. This is the cosmic friction term in the equation of motion of phi. A dot is 1. A goes to 0 near the beginning here. And so there's an enormous amount of cosmic friction here. That's rather useful in slowing down the inflaton and making sure that it doesn't slide off very, very quickly to infinity. I call this the overshoot problem, but I'm not exactly sure this is what everybody else calls the overshoot problem. I have a feeling the overshoot problem, as it was originally defined, had to do with rolling over the edge here. But this is another overshoot problem here that you could conceivably get into trouble where you just overshoot the inflationary region altogether. And that you're well protected. You're well protected against by this cosmic friction term blowing up and being very, very large in the beginning. All right, so that's a good thing. History of the universe, same history of the universe. Within the FRW patch, it starts out curvature dominated. Curvature dominated means that it's dominated by the term which is much bigger than the vacuum energy in here, or than the inflaton potential. And then eventually, the curvature term shrinks down until it becomes no bigger than the vacuum energy. When I say vacuum energy, I mean inflaton potential energy along here. And you enter into the slow roll region. Eventually, you come to reheating at this point over here, and becomes radiation dominated. Eventually, the surface of last scattering, and here we are up in here somewheres. The problem, of course, is that too much slow roll inflation would obliterate everything that came before. Obliterate in the sense of observable signal.
If bubbles happen to form close enough to one another, they can collide. If one or more bubbles collided with our universe in our distant past, this could have left a detectable signature. Astronomers are currently looking for signatures of bubble collisions.
It seems pretty lucky that the universe is how it is. It's just the right size, has just the right expansion rate, and has just the right particle properties to allow stars and planets and people to exist. The habitability of our universe is largely defined by the properties of the quantum fields that pervade all space. The quantum fields give rise to the particles that make up all matter and all forces, and if those quantum fields were a bit different, none of the familiar structures from atoms to galaxies would be possible. In fact, for most possible configurations of the quantum fields, no structures would exist at all. Fortunately, things are the way they are, although don't get too cozy. There's at least one mechanism that could rewrite the laws of physics across the universe. That mechanism is vacuum decay, and some physicists think it's inevitable. First, to give you a crude picture, vacuum decay looks like a bubble of annihilation that expands at the speed of light, rewriting the nature of the quantum fields as it passes. To understand whether or not this might happen, we first need to understand the quantum fields that it threatens. For that, let's try an analogy. Think of all space as being sort of springy at every point. As a simplistic example, imagine a rubber ring at each point. If you compress the ring in one direction, it bounces back and begins to oscillate around its equilibrium shape. But each ring is also connected to neighbouring rings, so it can transfer its oscillations, causing a wave to propagate through space. And there are other ways for the rings to oscillate. It has different vibrational modes. For example, it could twist back and forth on different axes, or deform in more complex ways. We can think of each quantum field as a set of these modes of oscillation, and each quantum field, each type of oscillation, has a corresponding particle, and that's the oscillation itself. Just like the deformed ring, a quantum field wants to return to its equilibrium position. That position is the field value where the energy is minimized. Physicists like to represent this by plotting the energy in the quantum field versus the field value. It takes more energy to get further away from the minimum, the equilibrium point. Just like it takes more energy if you want to deform the rubber ring. Another nice physical analogy is a ball rolling in a dip. The ball will roll up and down, oscillating around the equilibrium, and the height it reaches depends on how much energy it has. For most quantum fields, the minimum energy is where the field value is zero. For example, for an electromagnetic wave, a photon, the electric and magnetic fields rise and fall between positive and negative values, but the average field value is zero. And after the photon passes, the electromagnetic field goes back to zero. But there's one quantum field that breaks these rules. That's the Higgs field. The minimum energy state of the Higgs field is not where the field strength is zero. Instead, the Higgs field likes to settle into an equilibrium value where it has a real positive value. This means that the entire universe is filled with this soup of Higgsiness. Most elementary particles that have mass gain their mass due to interactions with this ubiquitous field. I go into all the details of the mass-granting power of the Higgs mechanism in a previous video. For today, all you need to know is that there's this one quantum field that has a minimum energy value where the field strength is non-zero, and this also means that the energy carried by the Higgs field is non-zero even at this minimum. And that's where the trouble starts. The Higgs field may have yet another weird property. It may have more than one possible minimum value. This would look like multiple dips in our graph of energy versus field strength. A quantum field with multiple minima like this will tend to find its way into one of these dips and get stuck there, just like a ball rolling on an undulating surface. In order to move between dips, the ball or the quantum field needs to gain enough energy to overcome this barrier between them. That could happen, say, in an extreme energy environment, like the Big Bang or near a black hole, or in a sufficiently large particle accelerator. But there's another way to make this jump. The Heisenberg uncertainty principle tells us that there's a fundamental uncertainty in, well, pretty much everything, but certainly in the value of a quantum field. This results in fluctuations in the field strength that can cause it to spontaneously shift and perhaps find itself stuck in an adjacent dip. We call this quantum tunneling. So what does this mean for the Higgs field? Well, some theorists do believe that the Higgs field has at least two minima, and those minima should have different energy values. There's a true minimum, the true lowest energy, or what we call the true vacuum. This is where the field would prefer to spend its time given the choice. And then there's another local minimum with a higher energy, what we call a false vacuum. The false vacuum is a so-called metastable state. It seems stable as long as the field doesn't learn about the more stable, lower energy state. Somewhat worryingly, we don't know which of these minima our universe's Higgs field is in right now. Let's think about the potentially catastrophic consequences of all of this. Firstly, if the Higgs field is in the true minimum, then no big deal. Even if the field at one location of space tunneled or was excited into the false minimum, it will quickly find its way back to the true minimum for reasons I'll get to. But what if the entire universe is in the false vacuum? Then a tunneling event would be a little more dramatic. Imagine a universe filled with the Higgs field in a false vacuum. At a single point in space, a quantum tunneling event drops the field into the true vacuum. This creates a tiny bubble that is at an energetically favourable state compared to the surroundings. The interior of the bubble immediately tries to drag the surrounding Higgs field down with it. This happens because quantum fields are connected and tug at their adjacent points across space, which is why their oscillations propagate as particles. Now, this isn't necessarily an instant disaster. The interior of the bubble wants to expand, but the shell of the bubble is actually in an energetically unfavourable state. It's in this unpleasant transitional state between the two minima of the Higgs field. In fact, the bubble wall experiences a sort of surface tension that tries to collapse the bubble again. Things get awkward if the initial bubble exceeds a certain size. The bigger the bubble, the more its interior wants to expand into its surroundings. But you also have more bubble surface, and so more surface tension to resist that expansion. But the interior of the bubble increases with the cube of the radius, while the surface increases only with radius squared. That means that above a certain size, the hunger of the bubble interior dominates. The bubble grows, and that growth very quickly approaches the speed of light. Once it gets going, the bubble is unstoppable and will drag the Higgs field through the entire universe down into the true vacuum. This is vacuum decay. It's a phase transition of the quantum fields. In fact, it has a lot of similarities with the sort of phase transitions that you get in matter. For example, when water boils, it undergoes a phase transition to water vapor. That phase transition also starts as small bubbles that grow into its surroundings. The formation of these phase transition bubbles in water or in a quantum field is called bubble nucleation. Okay, let's review the horrors that would result from vacuum decay. First up, everything gets fried. The energy released in the decay of the Higgs field fills the expanding bubble with a hot soup of energetic particles. It's similar to how the energy held in the latent heat of boiling water is released into the kinetic energy of gas molecules. But that's not the worst of it. As I mentioned, the Higgs field gives elementary particles their masses. Those masses depend on the energy of the field, the so-called vacuum expectation value. Drop the energy in the field and you reduce the masses of the elementary particles. The ability for stars to form and to undergo nuclear fusion, the ability for chemistry to work as it does, depends sensitively on the properties of the elementary particles. Life and structure could not exist as we know it, and may not exist at all. I should also add that there are other possible types of vacuum decay beyond Higgs field decay. For example, there may be weird fields within string theory that exist in false vacuum states. The decay of those could rewrite the laws of physics in far more drastic ways. This all sounds moderately bad, but can this actually happen? Well, first let's ask whether we really are living in one of these nasty false vacuums. Then we'll talk about whether that vacuum might decay. Assuming the Higgs field really does have multiple minima, the question becomes which minimum are we in? The true one or the false one? Well, it turns out that theorists aren't sure. We can determine the shape of the Higgs field with precise measurements of the particles that gain their mass from the Higgs. The most important are the Higgs particle itself, as well as the top quark, which is the most massive elementary particle. And our measurements of these masses tell us that we are probably in the false vacuum, but we're actually very close to the boundary. We might be in the true vacuum, which would be good, but it's a bit more likely that we're in the bad false one. Further study of the Higgs particle and the top quark should help us figure this out. Okay, so the next question is, could the vacuum really decay? Well, as long as decay is possible, it is inevitable. At any instant in time, there's a tiny but real probability that a patch of space will tunnel between the false and true vacuums. Wait long enough and it will happen. Happily, there's only a very small probability that a bubble of true vacuum will randomly form that's large enough to actually continue growing. Physicists have not converged on a single timescale. They vary from roughly the current age of the universe to 10 to the power of hundreds of times the age of the universe for a single such bubble to be likely to appear somewhere in our observable universe. So somewhere between vaguely unlikely and staggeringly unlikely. But before you get too comfortable, remember that there's another way to hop between energy minima. If enough energy can be pumped into a patch of space, the Higgs field can hop between minima without tunneling. This would be like dropping specks of dust into superheated water. Dust provides sites for bubble nucleation, and the entire body of water rapidly evaporates. Now, there was some fear that our giant particle colliders like the LHC might nucleate a vacuum decay bubble, but that was unfounded. After all, Earth is constantly being bombarded by cosmic rays of much higher energies than the LHC can produce, and no annihilation just yet. Overall, it's very unlikely that a vacuum decay bubble will reach us in the lifespan of our species, let alone our own lifetimes. Of course, in an infinitely or even sufficiently large universe, then vacuum decay has definitely started somewhere. But as long as we are far enough away, we're safe. If the vacuum decay starts beyond several billion light years, the accelerating expansion of the universe will throw us away from it faster than the bubble of annihilation can grow, even though that growth is nearly at the speed of light. And this leads to one more comforting fact. If the vacuum does decay inside our cosmic horizon, we will never see it coming, because no light can outpace the expanding bubble to warn us of its approach.
The best ways to solve problems in science can be, like borrowing from other kinds of science, because there are often surprising connections between disciplines that seem totally unrelated. Sometimes, though, these connections can go from unrelated to, far-fetched. That can't be a thing. Say slime molds predicting the shape of matter in the universe. And yet, in a paper published last week in the astrophysical journal Letters, a team of researchers claimed their model based on slime mold is so far our best predictor of the distribution of matter in the universe. The team was trying to predict the shape of the cosmic web, the thread-like network of matter that spreads through the whole universe. It hasn't always looked the way it does today, and understanding how the cosmic web has evolved over time is key to understanding the forces driving its structure. Go back to just after the Big Bang, and stuff was spread pretty much uniformly throughout space. Then gravity started to take over. Areas with a little extra density began to pull other material in. So denser areas got even denser, and less dense areas emptied out until a net-like structure formed. At dense spots where those strands intersected, clumps of matter eventually collapsed into the first galaxies, loosely connected by tendrils of gas and dust called the intergalactic medium. Because their stars give off light, astronomers today can map the locations of galaxies pretty easily, but uncovering the web has proven to be harder, at least until we got a little help from Physarum polycephalum, a slime mold. P. polycephalum is basically just one big cell, but for a single cell it is surprisingly complex. It has a bunch of nuclei but no brain, yet it can form memories and learn and even pass on that knowledge to other slime molds. Most important for the team of astronomers, though, is how it moves. When searching for food, the slime mold sends out bits of itself in all directions. If one part finds a source of food, it flourishes and the whole organism kind of grows in that direction. And that's not all that different from how clusters of matter grow, if you imagine that anything with gravity is like a source of food for the cosmic web. In fact, a postdoc at UC Santa Cruz realized that mathematically the evolution of the cosmic web was pretty similar to the growth of slime mold. So to apply this technique to the cosmic web, the team took a computer model for slime mold growth and modified it for the three-dimensional nature of space. Then they marked the present-day locations of galaxies as food sources and let the mold grow. The result was basically a map of possible connections between galaxies near and far. The stronger the link, the thicker the web. To check their results, the team compared these predictions with hundreds of observations made by the Hubble Space Telescope. And it worked. Where the slime mold model said there should be gas, there was gas. Where it said there should be a lot of gas, they found that too.
the final point of what we do. And the idea of how two frequencies can actually match, kind of duality, it came up in a very closely related context in this work of Malvicino in 1997. If you hit a concrete block, you just smash and you die. Okay, so that we know. But if you take these branes in string theory and you fall onto it, you oscillate the branes, and they have a certain set of frequencies. But it turns out that if you just had empty space with no branes, but something called anti-de Sitter space, a particular kind of curved space, the frequencies of vibration in that are the same as the frequencies of vibrations of D branes, and one exactly mimic the other. So you can actually replace branes with space, and that's called the ADS-CFT correspondence you might have heard about.
So quantum mechanics gets you from 0 to this small size, and once you get to this small size, then you're able to use general relativity and Einstein theory to generate all the rest.
Right.
Now, this is remarkable and awesome, but it is not something from nothing, because you're starting with the laws of quantum physics, you're starting the laws of general relativity. I mean, there's a lot of somethings there. This vacuum you talk about, as you said, is pulsing with energy and fluctuations and pressure and all sorts of things. I mean, there's a lot there.
That's true, but I'm not starting with the vacuum, right? Vacuum is what comes out of it. So what I'm starting with are indeed the laws of physics, of general relativity and quantum mechanics. And of course, and these laws are assumed to exist in some sense, in some Platonic sense, even prior to the universe, although prior I should put in quotation marks because there is no time. And the question, of course, is an extremely intriguing question of why these laws, who gives the laws, It's a deep mystery, and I don't have much to say about that. I would like to. Many things are possible that are not possible in classical physics. And indeed, you can have, in principle, you can have very strange things happening, like objects coming out of thin air. However, there are some rules, and these rules are conservation laws. So energy conservation is always enforced. For example, you cannot have a tiger appear out of in the vacuum, right? Because tiger has some mass, some energy. But if you have a lump of matter, in principle, it can turn into tiger. And quantum mechanics will not tell you that this is absolutely impossible, but if you try to calculate the probability of this happening, it will be pretty low.
Introducing Abell 2744. It's a giant cluster of galaxies around 4 billion light years away, basically our backyard, cosmologically speaking. The most interesting thing about Abell 2744, at least for us today, isn't what's in this cluster itself, but what's behind it. The cluster lives in a vast halo of dark matter that warps space across its 4 million light-year span. Light from distant objects travelling through the cluster is deflected and magnified. The cluster is a stupendous gravitational lens that enables us to see much further than our puny human-made telescopes would normally allow. That's why the Hubble Space Telescope studied Abell 2744 in detail, and why it was one of the early must-dos for the James Webb Space Telescope. And this is where our smudge got interesting. JWST observes deep into infrared wavelengths and showed that this object has IR colours consistent with a galaxy whose normally visible light has been stretched out by the expanding universe, increasing or redshifting its wavelength by a factor of over 10. Higher redshift means larger distance, and a redshift of 10.1 in this case means this light has been travelling to us for around 13.2 billion years, coming to us from a time near the beginning of time, when the universe was less than 3.5% its current age. That earned our smudge the name UHZ1 for Ultra High Redshift Galaxy number 1, where the Z is the symbol for redshift. That's cool, but JWST has now found galaxies quite a bit more distant than this. The really exciting moment came when we pointed another orbiting satellite at this smudge. This is the image by the Chandra X-ray telescope. It turns out there are a lot of X-rays coming from this little blob. Now, X-rays are much harder to bring to sharp focus So the 4 pixels of the X-ray light aren't coming from across this spread out region, but rather from something inside that region. There's really only one known way for a galaxy to be blasting out X-rays at this level, and that's by harboring a quasar. To refresh your memory, a quasar is when a supermassive black hole, an SMBH, that lives in the center of every galaxy starts feeding. As matter swirls towards the black hole, it's superheated until it outshines the entire surrounding galaxy. And just before it reaches the black hole, conditions get so crazy that the space outside the black hole glows bright with high-energy X-rays. Based on the amount of X-ray light and the distance, we can estimate that the black hole must be 40 million times our Sun's mass. That's 10 times the mass of the Milky Way's own SMBH. UHZ1 is the most distant quasar ever discovered, which makes it the earliest known quasar and so the earliest black hole that we have evidence for. So, with that out of the way, let's get to the good stuff. To understand why UHZ1 is so exciting, you have to understand one of the biggest debates in cosmology, the origin of supermassive black holes. Essentially, every galaxy in the modern universe has at its core a black hole that's 100,000 to several billion times the mass of the Sun. We also see much smaller black holes, so-called stellar mass black holes, that can be in the rough range of 10 to 100 solar masses. Oddly, we don't see black holes in the middle range of 100 to 100,000, and we'll come back to why that's odd. Now, we know how to make stellar black holes. They're what you get when the core of a massive star collapses on itself after the star dies. So, how do you make a supermassive black hole? That's the big question. It could be that they grew from the very first stellar corpses in the early universe, gulping down gas and merging with other black holes for billions of years to reach their current enormous sizes. But over the last decade or so, as we looked to greater and greater distances, we started to find quasars shining out from the first billion years of cosmic time, quasars powered by supermassive black holes that should not have had enough time to get that big. There are 2 potential solutions to this conundrum. Either black holes started small and grew way faster than we thought they could, or they started much bigger than the black holes that form in stellar deaths in the modern universe. These are the small seed and the heavy seed models respectively. UHZ1 is going to help us choose between them. Let's start with the small seed model. Can a stellar corpse grow into a quasar engine in less than 1 billion years? Well, it's tricky. There's a limit to how fast a black hole can feed, even with an endless supply of gas. As gas spiraling into a black hole heats up, it blasts out radiation which pushes on the infalling gas and counters the black hole's gravity. Bigger black holes can eat more and radiate more, but there's always an approximate upper limit that increases with that mass. It's called the Eddington limit. You can calculate how big a black hole would grow feeding at this maximum rate for, say, 1 billion years. And the answer is not big enough to explain those early quasars. That said, there are various tricks we can include to make the small seed model work. There are scenarios in which black holes can feed somewhat faster than the Eddington limit, although they still need to feed non-stop to reach supermassive status so quickly, which itself is a problem. Or you can form a lot of black holes close to each other and have them merge very quickly, or you can start out with really big stars that leave behind black holes that are maybe 100 or even 1,000 times larger than those produced today. In the modern universe, all the heavy elements released in past supernovae cause gas clouds to fragment as they collapse, leading to smaller stars. But the pristine hydrogen and helium that filled the universe in the beginning held together as it collapsed, probably leading to gigantic stars and commensurately massive, but still not supermassive, black holes. With a combination of these tricks, fast and consistent feeding and biggish stellar black hole seeds, it's possible to make supermassive black holes in under 1 billion years. This still doesn't explain why we don't see any black holes in the 100 to 100,000 solar mass range. If SMBHs grew from stellar black holes by passing through this range, then you'd expect some stragglers to still be in that range, but that doesn't seem to be the case. Okay, so let's try the heavy seed model. What if the seeds of supermassive black holes weren't even born from the hyperdense cores of dead stars? And in fact, it's actually a misconception that you need extremely dense matter to make a black hole. For any given mass, there's a particular size that mass needs to be crushed into in order to form a black hole. This is the Schwarzschild radius. For the Sun, it's around 3 kilometers, and a solar mass crammed within that radius would have the same density as a typical 3,000 meter tall mountain crammed into a cubic centimeter. On the other hand, a typical chonky supermassive black hole of 1 billion solar masses has a Schwarzschild radius the size of Neptune's orbit. 1 billion suns crammed into that region would have the density of cotton candy. That's right, fill the solar system with cotton candy and you'd get an instant giant black hole. The early universe did not contain significant quantities of cotton candy, at least as far as we can tell. But it was filled with a lot of gas that would later form stars and galaxies. As that gas started to collapse to make those things, the resulting protogalactic clouds may have had cores dense enough to collapse directly into black holes without ever forming a star. Again, this only works in the early universe where unpolluted hydrogen and helium doesn't tend to fragment as it collapses. And, as it happens, theoretical calculations of the expected sizes of these direct collapse black holes are right around the 100,000 solar mass mark. That gives us a way to go straight from gas to the smallest SMBHs without having to grow from stellar seeds through the intermediate range. And once you have a small SMBH, a pretty sensible rate of feeding can turn it into a large SMBH in mere hundreds of millions of years. Okay, great. Between our two models, small versus heavy seed, it's looking like the heavy seed model feels more plausible. So, let's see what the new player, UHZ1, has to say about this. Previous record holders for the most distant quasar, like J1342 plus 0928, J0313 minus 1806, and J1007 plus 2115, are all similarly massive, and they had already put the small seed formation theory under a lot of stress over the past few years. But they were all found right around the 700 million years after the Big Bang mark, just on the boundary of the amount of time needed to grow a small seed, assuming some very creative astrophysics to allow a really cosmic bulking phase. But UHZ1 shaves 200 million years off the allowed growth time. If it was marginally possible to grow a small seed into an SMBH before, it's now feeling nearly impossible. Let's look a bit more closely at this object to try to make this more concrete. Based on the JWST images, we can get an idea of the amount of starlight versus the quasar light in this object. Even those images are dominated by quasar light. The galaxy has around 40 million suns worth of mass in stars, the same as its mass in a black hole, and that's around 1,000 times less than the stars in the Milky Way. This isn't unusual in itself. We expect galaxies from so long ago to still be building up mass and converting gas into stars. But for most of the universe's history, we see a pretty tight correlation between the number of stars in a galaxy and the mass of the central black hole. That has been taken by some to indicate that galaxies and their central black holes grow together in relative lockstep. UHZ1 suggests otherwise. It tells us that the black hole starts relatively enormous and then the stellar mass catches up. UHZ1 may represent the very first in a new class of object called an OBG, for overly massive black hole galaxy or outsized black hole galaxy. OBGs are objects hypothesized to exist in the early universe in which the black hole and stellar masses are around the same. The amount of infrared and X-ray light coming from UHZ1 is consistent with simulations of OBG formation. So maybe this class of object is no longer hypothetical. If so, that tells us a lot. OBGs only work if their central black hole is formed by direct collapse, not through the growth of a stellar remnant. Overall, things are looking pretty good for the heavy seed model, but quite a bit less good for the small seed model. Now, it's not quite a smoking gun. For example, maybe UHZ1 is just weird. Perhaps it's SMBH formed in an unusual way, for example from a rare and massive primordial black hole, or in an exotic environment like a quasi-star. But the fact that observations of UHZ1 line up so well with the direct collapse and the OBG model would tend to disfavor these alternate explanations, at least in UHZ1's case. And even if UHZ1 is an OBG, it doesn't mean other supermassive black holes couldn't have formed from small seeds. But in general, the case for the latter as an important source for SMBHs is being whittled away. So what's next? Well, we keep looking. UHZ1 is the first of its kind, but in astronomy, where there's one, there's often many, and hopefully soon we'll find the many. As JWST and Chandra continue their good work, we'll develop a clearer and clearer picture of what the earliest times were like as we discover more distant glimmers of the earliest stars and quasars that first lit up a newly born spacetime. Another difference is the guiding equation in pilot wave theory. Many worlds doesn't need it because the evolution of the wave function alone only needs the Schrödinger equation. This guiding equation presents its own issues. The main one is that it needs to know about not just the corpuscle in question, but also every other corpuscle connected to it via entanglement. It needs this to ensure that all the corpuscles are always funneled into the one real world. This means that the guiding equation is explicitly non-local, causing instantaneous interactions between corpuscles across arbitrarily large regions of space. In fact, we now know that it's impossible for any hidden variable theory, like pilot wave theory, to preserve locality.
What is now the explanation of what really happens in these galaxies? I already told you that the observations tell us that this acceleration, when it drops below this number, actually tells us that that's where dark matter effects become important. This is where rotation curve starts flattening. This is actually rewritten in terms of a quantity which I call, this is actually the Bekenstein entropy that I introduced in the beginning. And this is the entropy that's actually contained in the dark energy. So the picture is like this. This is the entropy that's carried or actually taken away by matter inside a certain region. So I take a certain region of size r, then the entropy associated to this mass is given by the Bekenstein formula. The entropy associated with the dark energy is by this volume law that I already indicated. And it's precisely when this drops below that we start seeing the deviations. And this is where the dark energy starts taking an effect and actually pushes back. And this is what you can calculate. And I'll show you just some plots at the end of this talk. I mean, there's some way that you can calculate when the amount of matter that you put in, actually it reduces the amount of dark energy. It actually reduces the amount of entanglement. It's sort of like removing part of a medium. And there's an elastic response. These are pictures from the paper I wrote on this. And the entropy actually changes the nature of gravity because actually there's a volume law that takes over.
In fact, any equation of state parameter less than -1/3 would cause that effect. It would mean the stuff is diluted away a little less quickly than the universe expands. In fact, if the parameter is below -1/3 but larger than -1, that's still accelerating expansion, but in that case the dark energy is decreasing over time. The popular idea for that scenario is called quintessence, and it's something for a future episode. For today, let's push things to the limit. What if we make the equation of state parameter smaller than -1? How about -1.5, -3, -1,000,000? That's the case where the density doesn't just stay constant as the universe expands, but it actually increases. The result would be that the acceleration increases over time. Offhand, that doesn't sound so much crazier than regular old dark energy, except that it is much crazier. As the rate of expansion increases, and with no gravitational bodies left to resist the expansion, all points in space will eventually be racing apart from each other faster than the speed of light. That faster than light recession of space is already happening, but right now for patches of space very far apart, like many billions of light years. If two patches of space are moving away from each other faster than light, then they can never communicate with each other. The distance from us to the nearest inaccessible region of space is called the cosmic event horizon. Now, if the expansion is accelerating, then over time, the distance between patches of light speed space gets smaller. And that is actually happening. Your cosmic event horizon gets closer and closer. Eventually, we won't even be able to see the nearest galaxies because they'll be moving away too quickly. But as long as we have a nice gravitationally bound galaxy to live in, the cosmic event horizon can never shrink to a size smaller than that galaxy. That's not the case if dark energy increases. After our galaxy is disrupted by the increasing dark energy, there's no protection from the encroaching cosmic event horizon. The final result is that no particles will be close enough to interact with each other, ever. So protons and neutrons will be separated into their component quarks. That is the Big Rip scenario. It happens when the cosmic event horizon is smaller than the smallest possible structure. What could cause something like this? No idea. No one has any idea. That doesn't stop us from giving it a name. We call any dark energy that increases in strength, so with an equation of state less than -1, phantom energy. That name seems to have been coined by Dartmouth physicist Robert Caldwell in a seminal 2002 paper, The Phantom Menace. And that was 3 years after the theatrical release, and I guess we still thought it was a sign of the end of the universe. So, let's see what this made-up math has to say about when the Big Rip would happen. Any equation of state parameter smaller than -1 means a Big Rip. The smaller the parameter, the sooner it happens. Caldwell does this calculation for the case of W equals -1.5. In this scenario, the Big Rip happens in 22 billion years from now. Things don't get really messy until near the end. Around 1 billion years before the Big Rip, galaxy clusters are ripped apart. At 60 million years and counting, the Milky Way is shredded. Now, this doesn't mean that the cosmic event horizon is quite inside the Milky Way just yet, just that the effect of phantom energy is stronger than the gravity binding the stars together. In fact, at this point, the cosmic event horizon is still about 200 million light years away, and so there should be a handful of galaxies still visible to us. There are some millions of years of fun as we watch those galaxies disassemble and the constellations of stars in the Milky Way fly apart. The final deadly stage only happens in the last month or so when the solar system is pulled apart. In the last 30 minutes, phantom energy is strong enough to overcome Earth's own gravitational binding energy, and the planet is disrupted. Moments later, at the 10 to the -19th of a second before absolute disruption, it will overcome all chemical bonds, then the forces binding atoms together, then nucleons, and then presumably anything smaller. In its final state, a Big Rip universe will be nothing but hopelessly isolated elementary particles separated by infinitely expanding space.
When we observe light from distant galaxies, we are seeing the light from the stars in those galaxies, and that light has absorption lines. The same lines, measured in a lab, give us the wavelength of the light at the time it was emitted. What we observe is the wavelength stretched over the time it took to get here. We define redshift, z, as the difference between the two divided by the wavelength emitted. In this hypothetical example, we have an object with a redshift equal to 6. Once a model for the change in the cosmic scale factor over time is specified, redshift gives us a great deal of information. For now, we'll assume a flat, matter-dominated, Einstein de Sitter universe. This will only get us part of the way to the actual numbers, but it helps illustrate the key role redshift plays in cosmology. First, redshift gives us an object's receding velocity. With our model, we have the object moving away at 6 times the speed of light. Redshift also gives us the actual cosmic scale factor at the time the light was emitted. It gives us the age of the universe at the time the light was emitted. And it gives us the amount of time the light was traveling. Redshift gives us the distance to the object at the current time, and it gives us the distance to the object at the time the light was emitted. You can see why astronomers rely so heavily on redshift measurements. Next, we'll use it extensively to count galaxies.
The lower dimensional CFT space is the surface of the ADS space because the field theory exists where that new dimension becomes infinite, infinitely far away.
And so each energy scale, as in standard in ADS-CFT, so energy scale or length scale corresponds to radial evolution of anti-de Sitter space. So we call Z, but Z is actually exponential minus U. So this is a U direction, and this is a more precise Z direction of the ADS-CFT interpretation, so length scale direction. And this time evolution here. And then we do this quench and see how this chi U evolves, this entanglement base. This is just free scalar fields, but actually it may be a little bit surprising. We see some analog gravitational wave because this chi U is how much entanglement we add, and it is directly related to metric perturbation because entanglement entropy is related to the area of the spacetime. But here we should be very careful. This is a free theory, so we don't have a standard area safety. But anyway, so we have some analog of this gravitational wave and this analog of light cone, though it's not precisely equal to the light velocity one. So that way, anyway, we can see some analog of dynamics of this emergent dynamics from this network calculations.
If I take a little quark and I magnify it, conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament of energy, a little string-like filament. And just like the string on a violin, I pluck it and it vibrates, creates a little musical note that I can hear. The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves.
Now I'm going to turn on 2,000 volts.
What?
This is the first step in creating snowflakes in the lab.
This is totally wild. What?
Crazy, huh? The tips of those needles are like 100 nanometers in diameter.
That is so wild.
Dr. Ken Liebrecht is the snowflake guy.
I was the snowflake consultant for the movie Frozen. It's okay to conjure snowflakes out of your fingertips, but they have to be real snowflakes or people aren't buying it. The U.S. Post Office made snowflake stamps using my pictures. It's not the kind of thing you normally think of when you start doing physics, that you'd be on a postage stamp.
You've written the book on snowflakes, literally.
So I had like 2 successful books in a row. So we just kept making books until finally they sold 0 copies, and then we stopped.
So you're kind of like a snowflake artist.
I call it a designer snowflake. Because yes, I am designing this on the fly. I don't have a computer that does all this for me, I just do it by hand. So everyone's a little different.
Ken knows so much about snowflakes, he can design and construct them to his own specifications.
So what's happening now is it's growing and doing its thing. It's at minus 13 Celsius now, but I want to make some branches. I'll just turn this down to minus 15. And then I'm going to increase the humidity a little bit, the supersaturation, and you'll start to see branches come out there.
So you changing those conditions just caused the plate to kind of stop and become really...
I changed the growth conditions to prefer branches. This little thing right there, that little nub, that's the only thing that touches the sapphire substrate. The rest of this is all growing above. This increases the airflow. Those are droplets forming, and now I'm really kicking it into gear. Now what I'm going to do is I'm going to turn that humidity down to 0, so the droplets are starting to recede. And this will stop growing and kind of start to facet a little bit. Say, I want branches again. And now I'm going to really hammer on it.
So you're giving it a lot of moisture.
A lot of moisture now. But you'll see side branches. You really start to feel you understand what's going on when you can say, now I'm going to do this. And then it happens. It's fun. I can predict the future. I like to think they're better than nature. And the reason is that the facets are just sharp. All the edges on these things are just sharp and crisp. Whereas in the sky, they have to fall. And by the time they fall and you pick them up and you put them under a microscope, they've started to evaporate a little. Boy, these are just bang, just crisp.
The first close-up photograph of a snowflake in the wild was taken in 1885 by American meteorologist Wilson A. Bentley. It was Bentley who originated the idea that no 2 snowflakes are alike. And he would know. Over the course of his life, he took more than 5,000 photos of snowflakes, a selection of which appear in his book Snow Crystals, which is still in print today. But most snowflakes don't look like the ones Bentley photographed, because he selected only those in pristine condition, with uncommon beauty and symmetry.
I mean, when you're looking for snowflakes, I'll take a big piece of cardboard, and you just glance at it. Crap, nothing. Brush them aside, more. No. Each brush is 1,000 snowflakes. They're hard to find. You can't, they're 1 in a million. I mean, literally.
We are all so used to seeing pictures like this that we are blind to the mysteries of the snowflake. Like, why do they all have 6-fold radial symmetry? Why are they so intricate and yet so different from each other? How do opposite arms of a snowflake mirror each other so perfectly? I mean, how does one side of the snowflake know what the other side is doing? And why are snowflakes flat? They're usually millimeters in diameter, but micrometers thick. The edges of a plate can be as narrow as razor blades. But the mystery goes even deeper. Everyone pictures snowflakes like this, but the truth is they take all sorts of different forms. Like this, a hollow column.
That is a snowflake?
That is a snowflake.
There are also needles, cups, and bullets.
This is like my favorite kind of snowflake, is a capped column. It started out growing as a column, but then the temperature changed and then you've got plates growing on either end. It's just a cacophony of different shapes. All of these appear spontaneously. There's no DNA or any kind of blueprint for what's going on. It's just water vapor freezing into ice, and all this happens.
So you've identified 35 different types of snowflakes.
Yes, there's no really one way to define a type of snowflake. The first chart of snowflakes is like 41, I think, and then it got bigger and 60 or 70. And the latest one by some Japanese physicists, I think, had 108 different types of snowflakes. And I found 108 was too many.
How does simple ice create so many distinct forms? All snowflakes form in much the same way. Water evaporates into water vapor, individual molecules bouncing around in the atmosphere. And as this vapor rises, it cools and becomes supersaturated, meaning there are more water molecules in the air than there would be in equilibrium at this temperature. Water molecules condense onto dust particles to form tiny droplets. And although the temperature may be below freezing, the droplets don't immediately freeze. But at some point, one droplet will freeze. Inside, the water molecules lock into place, forming a hexagonal crystal. This structure results from the peculiarities of water molecules. Oxygen atoms attract electrons more than hydrogen, and since the molecule has a bent shape, it's polar, with oxygen being slightly negative and the hydrogens slightly positive. Since unlike charges attract, hydrogen from one molecule will sit next to an oxygen from another molecule, forming a so-called hydrogen bond. And this is what creates the hexagonal molecular lattice. But how does this microscopic lattice grow into a hexagonal crystal that we can see?
So you start with a chunk of ice, and these little guys are meant to be water molecules. And what happens is there are these flat surfaces, which are the facet surfaces, and at a molecular scale, they're very smooth and flat. And so when a molecule hits, a water vapor molecule hits that smooth and flat surface, it tends to bounce off. Whereas here, it's rough. There are a lot of dangling molecular bonds over here. That's a rough surface. And so when these molecules hit, they tend to stick. It's a statistical thing, of course, but the probabilities are high that they stick here and low that they stick here. So if you take any shape and you just let it grow for a little while, the rough areas fill in and the flat areas don't grow very fast, and you end up with a faceted shape.
And that's how we get from the quantum mechanics that governs a water molecule to a hexagonal prism of ice. This prism has 2 basal facets and 6 prism facets, which is important. If the basal facets grow fast, you get a column. If the prism facets grow faster, you get a flat snowflake. Once there is a seed crystal, nearby water droplets evaporate and deposit water molecules onto the growing snowflake. Since the corners of the hexagonal prism stick out farther into humid air, they grow faster. And now they extend even farther, so they grow even faster in a positive feedback loop. This gives rise to 6 radial branches. At the corners of these branches, additional branches can form for the same reason. Around 100,000 droplets are required to make a single snowflake, and the process usually takes 30 to 45 minutes. In the 1930s, Ukehiro Nakaya was systematically studying snowflakes at the University of Hokkaido in Japan. He discovered that the different types of snowflakes don't all occur under the same conditions. Instead, 2 factors, the temperature and level of supersaturation, determine what type of snowflake grows. His findings are summarized in the Nakaya diagram, but it's not a simple pattern. Around -2 Celsius, you get plates. At -5 Celsius, columns and needles form. At -15 Celsius, it's plates again. And then below -20, you get columns and plates. The Nikaya diagram allows us to understand a rough history of any snowflake.
Does each snowflake, in essence, reveal its history through its shape?
Yeah, absolutely, to some degree. You can definitely look at a snowflake and say, yeah, I know what conditions that crystal grew under, more or less. Typical weather patterns, fronts, cold front. That produces a lot of capped columns because as the cloud moves up, it starts to get colder and initially start to freeze at around -6, -10. That makes columns. And as it gets colder, then it makes branches and plates, and so you get capped columns.
This also explains why snowflakes are so intricate. The temperature and humidity at each moment of growth determines the structures formed in that moment. The symmetry you see is not because one side somehow knows what the other side is doing, but because both sides of a single snowflake grow in the exact same conditions.
When the crystal changes its position, the temperature will change, say, and in all 6 branches we'll see the same temperature change, and so they'll all respond the same way.
Different snowflakes, on the other hand, each take a unique path, and therefore they experience a unique set of conditions, which is why no two snowflakes are alike. But in the lab, you can carefully control the conditions, so theoretically it should be possible to create almost identical snowflakes. And indeed, Ken has.
What's in here?
Poke your flashlight in and you'll see.
Uh-huh. I'm imagining these are seed crystals of a sort?
Those are little sparkly snow crystals.
Yeah.
You know, this is another little chamber, just a cold plate. And there's a little sapphire disc in there. And then I'm going to push this thing, my sapphire, all the way in here, and the crystals will waft onto it and hopefully stay there. The idea popped in. It's like, oh, if I grow 2 next to one another, they'll be kind of identical. And I call them identical twin snowflakes because they're like identical twin people. They're not exactly the same, but clearly more alike than you would ever expect. Is it really true that no 2 snowflakes are alike? And yeah, it's just a silly question. It's silly because no 2 trees are alike, no 2 grains of sand are alike, no 2 anything are alike. Anything that has any complexity is different from everything else because once you introduce complexity, then there's just an uncountable number of ways to make it.
If a pair of twin snowflakes are growing too close together, they end up competing for moisture between them, stunting both of their growths.
The Nikaya diagram allows us to understand a lot about snowflake formation. Ken has used his experiments to build his own version of the chart. But what it doesn't explain is why do ice crystals form this way in the first place? I mean, why do we get plates and then columns and then plates and columns again? This has been a mystery essentially since Nikaya introduced his diagram back in the 1930s. But Ken believes he now has an answer. Anytime you have a crystal, the reason why you get these smooth, flat facets is because it's not easy to grow more crystal on top. There are so-called nucleation barriers. What you need is a critical density of additional molecules of the substance before they can come together to form a little island that is stable enough to grow and add another layer onto the crystal. When you're first forming a snowflake, you're always going to start with a hexagonal prism with its 2 basal facets and 6 prism facets around the side. And the nucleation barrier for the basal facets is different than that of the prism facets. If the nucleation barrier is lower for the prism facets, then they grow faster and you get plate-like structures. If the nucleation barrier is lower for the basal facets, then they grow faster and you end up with column-like structures. Now, the nucleation barriers of ice are known as a function of temperature, and this explains why around -2, the prism facets grow faster and you get plates because their nucleation barrier is lower. You can also see why below -20 or so, well, then you get columns because the basal facet nucleation barrier is lower at those temperatures. But what doesn't make sense is why we should get columns at around -5 Celsius and then plates again at -15. So what is happening? Well, Ken's hypothesis is that these nucleation barriers are valid only for large, flat facets. But if you had really narrow facets, well, the nucleation barriers would be different. So Ken proposes that narrow basal facets have a dip in their nucleation barrier around -4 Celsius, and narrow prism facets have a dip at -15. So his hypothesis is that the graph should look like this. This then is consistent with all the different forms of snowflakes that grow at different temperatures. But what accounts for these dips? Well, let's say we have a narrow prism facet, so we're growing a plate snowflake. Water molecules that hit the basal facets are unlikely to reach the critical density required to overcome the nucleation barrier, so that surface grows only slowly. But on either side of this narrow prism facet, water molecules can stick on the rough edges. And to minimize surface energy, the ideal shape of this face would be semicircular. But if only the top few layers of water molecules are mobile, to try to lower the surface energy, many of them diffuse onto the prism facet. And in the process, they exceed the critical density required to overcome the nucleation barrier, and so they can grow the crystal on the prism facet. So due to this narrow edge, the nucleation barrier is effectively lower than it would be for a large prism facet. A similar effect happens for the basal facets, just at a different temperature. And Ken has done experiments to investigate whether these effects are observed in the lab.
And so I did a series of experiments using that apparatus, and man, it just like, boom, just like that. Whoa. When you make a model and you sort of find it's supposed to do something, and it sort of does, it's just like, this might be right.
So far, the results agree nicely with the hypothesis. So after 85 years, maybe we now understand the molecular physics of ice well enough to finally explain why snowflakes grow into such a diverse collection of columnar and plate-like forms.
I've done a lot of my career in astronomy and astrophysics. Nobody ever asked you what it's good for. I mean, never, not even once did anyone say, what are those black holes going to be used for? No. Saturn's rings. Why do you care about Saturn's rings? What's the motivation for studying Saturn? Nobody asks that. Every time I give a talk, people are like, what are you doing? What on earth is this for? I'll tell you the real reason that I got into this. You look at a snowflake and you kind of go, actually, we don't have any idea how that works. Well, that doesn't work. We have to know how that works, damn it. Well, I want to be the guy who figures out how snowflakes work. That's always been a driver, As a scientist, you want to figure something out.
Other image I had. Quickly, where's the galaxy? It's the middle, yeah, but the pictures are very similar. I claim the physics is kind of similar, same. This is, of course, anyway, this is a tornado. This is just a whirlpool. But I think there's something missing here, because we know here there's lots of things happening around it that are basically pulling these things. And maybe there's something there as well.
So I want to sort of lay out some sort of misconceptions that are often there about ADS-CFT and try to say why they're not true. And one is that ADS-CFT only holds for a subset of supersymmetric or BPS observables, and that's not true. There are a large number of the whole spectrum, the correlations, and we'll give examples why this is not true. But then there's another complaint that, oh yeah, maybe it's not just for supersymmetric observables, but we are looking at only observables in a supersymmetric theory. The theory has an underlying supersymmetry, which is what explains a lot of the magic. But as I tried to give next to mention in the list, there are by now several non-supersymmetric examples where we see such a duality. If not for supersymmetries, sometimes people raise the issue that maybe it's not supersymmetries, but all the isometries of ADS space, or equivalently the conformal symmetries, that are really what constrain the theory. And correspondence is essentially kinematic. It is the fact that the ADS D+1 and the conformal field theory share the same symmetries that essentially determines things. That's, again, far from being true. And there are many theories. The kinematics constrains things to a very mild extent. There are many quantities that are not at all constrained by the kinematics, which by now have been matched beautifully. And the related this thing is that it holds only for exactly conformal theories or exactly anti-de Sitter spacetimes, but this is also not true. There are massive theories, like I mentioned, and asymptotically ADS geometries. So this is also not necessarily the case. And as I tried to emphasize in the previous slide, the bulk theory is not always Einstein gravity or supergravity. And that's just a small corner, and that's often the corner a lot of people have been focusing on. But to really understand this correspondence, you need to look at the very least, the two-parameter, the two-dimensional space that I had in the previous slide. And and you need to both move. You need to move away ultimately from both the from this corner, both in the vertical as well as in the horizontal directions. And finally, sometimes people sort of say it's just a conjecture, but once again, I think the sheer weight of the evidence that has been there in the last 25 plus years, and in the wide variety of examples that I mentioned, indicate that this is just not true. There's by now as compelling evidence that this is not a seriously doubted thing by anyone who has worked in the subject. And the question is to understand the scope of this duality. And so ADS-CFT in some sense is here to stay. And this is regardless of what one might believe about string theory as a framework for quantum gravity and so on. In this limited context of asymptotically anti-de Sitter spacetimes, string theories give a consistent quantum gravitational description of large N gauge theories. It's a very non-trivial statement about large N gauge theories, and it is in a proof of concept that there are holographic quantum gravitational descriptions, at least for this class of spacetimes.
Caldwell does this calculation for the case of W equals negative 1.5. In this scenario, the Big Rip happens in 22 billion years from now. Things don't get really messy until near the end. Around 1 billion years before the Big Rip, galaxy clusters are ripped apart. At 60 million years and counting, the Milky Way is shredded. Now, this doesn't mean that the cosmic event horizon is quite inside the Milky Way just yet, just that the effect of phantom energy is stronger than the gravity binding the stars together. In fact, at this point, the cosmic event horizon is still about 200 million light years away, and so there should be a handful of galaxies still visible to us. There are some millions of years of fun as we watch those galaxies disassemble and the constellations of stars in the Milky Way fly apart. The final deadly stage only happens in the last month or so when the solar system is pulled apart. In the last 30 minutes, phantom energy is strong enough to overcome Earth's own gravitational binding energy and the planet is disrupted. Moments later, at the 10 to the negative 19th of a second before absolute disruption, it will overcome all chemical bonds, then the forces binding atoms together, then nucleons, and then presumably anything smaller.
Imagine a huge pot of boiling water. Bubbles of water vapor form at random times and random places. This is very similar to how bubble universes form, except instead of water, they form in the inflating false vacuum background.
So in this sense, there are sort of two senses of what people mean by the word Big Bang that tend to get conflated with each other. One of them is this hot thermal equilibrium boundary condition for the expanding universe. And in a very real sense, inflation takes place before this time. And inflation is a zero temperature Bose-Einstein condensate that then later decays and heats up the universe in the reheating process and brings the universe to thermal equilibrium. That happens at the end of inflation. On the other hand, in a standard Big Bang cosmology, that the hot radiation-dominated early universe is cut off by the initial singularity.
that the universe and everything in it, including us and all living things, the whole planet, every star, every galaxy, and even things outside the visible universe, are all connected. Everything, even our thoughts, dreams, and ideas, are composed of excitations in the same quantum fields. And all these fields extend to not only all of space, but all of time. The universe is made of the same basic stuff, and we are all simply a series of excitations in it. So when someone
the maximum amount of information that can fit in a volume of space is not proportional to that volume, is proportional to the surface area of that region of space. Jacob Bekenstein figured this out by realizing that the entropy of a black hole is proportional to the surface area of its event horizon. But entropy is just a measure of hidden information, so the Bekenstein bound is equally a limit on how much information you can fit into any region of space. We'll come back to the Bekenstein bound in a sec, but for now let's think about why this dependence on surface area is surprising. Well, common sense would suggest that the maximum information content depends on volume, not surface area. I mean, a pile of thumb drives has a total storage capacity that depends on its volume. But instead of storage capacity, let's think about the information needed to perfectly describe a patch of space. You'd think that to fully describe, say, the universe, you'd need to know what's going on in every tiniest possible 3D chunk. That smallest element is roughly a cube, 1 Planck length on a side, where the Planck length is the smallest meaningful measure of distance at around 1.6 times 10 to the negative 35 meters. It's the smallest possible chunk of space, so let's say it can contain the smallest amount of information, 1 bit per Planck volume. That's kind of like saying we can describe the universe completely if we go through all of its quantum voxels and answer the yes-no question of whether it's full or empty. This probably way underestimates how much info you really need to describe the universe, but let's start with this anyway. So, how many Planck volumes are there in the universe? Well, the radius of the universe is something like 47 billion light years, which is a few times 10 to the power of 61 Planck lengths. 4 on 3 pi r cubed, so the universe contains 10 to the power of 183 Planck volumes. You'll see estimates that the radius of the universe is a mere 10 to the 60 Planck lengths rather than 10 to the 61, and that its volume is 10 to the power of 180 units. And that's because cosmologists tend to round down at every step and so drop a bunch of orders of magnitude. Astrophysicists are, by comparison, highly accurate. We only drop factors of 2. But what's a few orders of magnitude between friends? You might argue that more than one bit can fit at each grid point in the universe. You might be right. Particles have more information than just their position. It will be better to use the number of grid points in quantum phase space, which includes position, but also other degrees of freedom like momentum, spin direction, etc. In other words, we should count all possible quantum states in the universe. Anyway, the real number is going to be way higher than our estimate of 10 to the 180, but as we'll see, we're already way higher than the actual information limit of the universe. Okay, so 10 to the power of 180 or so bits is the minimum if you want to describe every 3D quantum voxel completely independently. But the Bekenstein bound tells us that the information content of any volume isn't the number of these Planck volumes, but rather the number of Planck areas on the surface. The observable universe has a surface area of 10 to the power of 120 to 10 to the power of 124 Planck areas, depending on whether you're rounding like a cosmologist or an astrophysicist. So the storage capacity of the universe is around 10 to the 60 lower than the number of volume elements it contains. So how do you encode a whole universe in a space far smaller than the universe itself? There must be some amazing compression algorithm. Maybe middle out? In fact, in a sense, the holographic principle is a compression algorithm. See, you don't really need 1 bit per volume element of the universe. That would be like having separate, completely independent memory elements for every empty pixel in an image file. Most of space is indeed empty. Let's say instead you only need a single bit of information for every element in phase space that's occupied. In other words, 1 bit per elementary particle. The observable universe contains something like 10 to the power of 80 protons. Each proton has 3 quarks, and there are a similar number of electrons. Most other particles are much rarer, so we're still in the realm of 10 to the 80 to 10 to the 81. Neutrinos and photons formed in the Big Bang are probably a billion times more abundant than protons. That's verified experimentally in the case of photons. The cosmic microwave background has around 10 to the power of 89 photons across the observable universe. So almost all of the information, and for that matter the entropy, in particles is in neutrinos and in the cosmic microwave background photons. The situation with dark matter is unclear, so let's just round up to 10 to the power of 90 bits of information in particles in our universe. That sounds like a lot, but happily it's way less than the 10 to the power of 120-ish limit of the Bekenstein bound. But there's one more source of information: black holes. As I mentioned last time, black holes contain most of the entropy in the universe. The relationship between black hole entropy and information deserves some thought. Black hole entropy, in terms of number of bits, tells you the information you'd need to describe all possible initial states that could have possibly formed the same black hole, of which there are many, 2 to the power of the number of bits of entropy. And for black holes, that entropy is the Bekenstein bound, the number of Planck areas on its event horizon. Because the information about the black hole's previous state is lost, to fully describe it, you need to fully describe its event horizon. You need its full Bekenstein bound in information. How much information is that? Let's take a supermassive black hole as an example. Sagittarius A star in the center of the Milky Way, which has a mass of 4 million suns. Its event horizon is around 12 billion meters, giving it a surface area of 10 to the power of 90 to 10 to the power of 91 Planck units. So the Milky Way's black hole has as much entropy and hidden information as all of the matter and radiation in the entire rest of the universe. teach you how to use the same tool that physicists use. It's a tool that will let us easily answer the most common questions about black holes. For example, are objects falling through the event horizon really physically frozen there from the point of view of the outside universe? Would you see the entire future history of the universe play and fast forward at the instant that you crossed the event horizon? And do you see anything at all once you're inside the black hole? The tool that will answer these questions is called the Penrose diagram, sometimes also the Carter-Penrose diagram. It's a special type of space-time diagram designed to clarify the nature of horizons. But first, a quick refresher on basic space-time diagrams. By graphing time versus just one dimension in space, we can look at the limits of our access to the universe due to its absolute speed limit, the speed of light. With the right choice of space and time units, the speed of light becomes a diagonal line on the space-time diagram. The area encompassed by these so-called light-like paths defines all future events, all space-time locations that we could potentially travel to or influence, constrained by the cosmic speed limit. That's our forward light cone. Our past light cone defines the region of the past universe that could potentially have influenced us. Let's drop a black hole onto our space-time diagram. It lives at x equals 0 on the space axis, but exists through all the times on the graph. It has a point of infinite density, the singularity, and an event horizon a bit further out. The mass of the black hole stretches space and time, so that light rays appear to crawl out of the vicinity of the event horizon before escaping to flat space-time, no longer following 45-degree paths. Now, let's throw a monkey into the black hole. As it approaches the event horizon, its future light cone bends towards the black hole as fewer and fewer of its possible trajectories lead away. Below the event horizon, all possible trajectories lead towards the singularity. The problem with the regular space-time diagram is that the path of light and the shape of the light cone changes as space-time becomes warped. That makes it difficult to figure out what parts of the past and future universe the monkey can witness or escape to. And this is where the Penrose diagram comes in. It looks like this. It transforms the regular space-time diagram to give it two powerful features. It crunches together or compactifies the grid lines to fit infinite space-time on one graph. Very useful for black holes. It also curves the lines of constant time and constant space in what we call a conformal transformation, so that light always follows a 45-degree path. That means light cones always have the same orientation, everywhere. Super handy for understanding monkey trajectories. This is the Penrose diagram for flat space-time with no black holes. Same as with the regular space-time diagram. Blue vertical-ish lines represent fixed locations in one dimension of space, and red horizontal-ish lines are fixed moments in time. Now those lines get closer and closer together towards the edge of the plot to encompass more and more space-time. They're extremely finely separated at the edges, so that any tiny stretch on the graph represents vast distances and/or times. The lines also converge together towards the corners, so that light travels a 45-degree path everywhere on the diagram. So a light ray starting from really far away and coming towards us hugs the edge of the diagram and crosses an enormous number of time and space steps, only reaching us in our very distant future. Okay. Let's drop a black hole into this space-time. Nice and safely far off to the left. And because we only have one dimension of space, any motion to the left brings us closer to the black hole. Its event horizon becomes the end of the line in that direction. The future cosmic horizon on the Penrose diagram is replaced with a plunge into a black hole. The compactified grid lines there now represent the stretched space-time near the event horizon. An entirely new Penrose region represents the interior of the black hole. Weirdly, the lines of constant position and constant time switch. Space flows at greater than the speed of light inwards towards the central singularity. It becomes unidirectional, flowing inexorably downwards, just as time flowed inexorably forward in the outside universe. All paths lead to the inevitable singularity. Once you're beneath the horizon, your future light cone still represents all possible paths that you could take. All of them end up at that singularity. The only way to escape back to the outside universe would be to widen your light cone by traveling faster than light. So you're out of luck. I only showed you half of the Penrose diagram. The complete mathematical solution for a Schwarzschild black hole has two additional regions. One corresponding to a parallel universe on the other side of an untraversable wormhole, the Einstein-Rosen bridge. And down here we have what we call a white hole.
So let me try to explain how that happens using an analogy. So imagine a sentence. So we come back to this idea of a sentence. And the sentence says, if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. Now, when you heard this sentence, you probably in your mind divided it into various words, and then you probably grouped the words in some way, analyzing the grammar of the sentence and so on, and the meaning of the sentence. You found the various sub-sentences or sub-clauses and so on, and until you got the full sentence. So in fact, there were also long-distance correlations, for example, between the word man, his, and he, or between the concept of keeping pace and drummer. Okay, that's a kind of deeper level correlation. As we include more words in our analysis, we get to a deeper meaning of the sentence. Okay? So we have, in some sense, an extra dimension, which is the depth of meaning, or the direction of meaning in the sentence, of how deeply encoded is a particular concept within this sentence. So in this analogy, the idea is that the state of the quantum system is analogous to a very long sentence that lives at the boundary. And the bulk geometry is doing some analysis of the meaning of this particular sentence. So that's in the analogies, reflecting the correlations that you have between the various words of the sentence, and there are correlations that are encoded that involve short distances along the sentence, and some involve words that are very far away in the sentence. And for example, particles in the space-time could be particular words that are either repeated or have some correlated meaning in the sentence.
But the funny thing about quantum objects is that they can be in both states at once. Now, when you measure the spin, it will be either up or down, but before you measure it, the electron can exist in what's called a quantum superposition, where these coefficients indicate the relative probability of finding the electron in one state or the other.
Now, it's hard to imagine how this enables the incredible computing power of quantum computers without considering two interacting quantum bits. Hello. Hi. Now there are 4 possible states of these two electrons.
You could think that, well, that's just like 2 bits of a classical computer, right? If you have 2 bits, you can write 00, 01, 10, 11, right? There's 4 numbers. But these are still just 2 bits of information, right? All I need to say to determine which one of the 4 numbers you have in your computer code is the value of the first bit and the value of the second bit. Here instead, quantum mechanics allows me to make superposition of each one of these 4 states. So I can write a quantum mechanical state which is perfectly legitimate, that is some coefficient times this, plus some coefficient times that, plus some coefficient times that, plus some coefficient. So to determine the state of this 2-spin system, I need to give you 4 numbers, 4 coefficients. Whereas in the classical example of the 2 bits, I only need to give you 2 bits. So this is how you understand why 2 qubits actually contain 4 bits of information. I need to give you 4 numbers to tell you the state of this system. Whereas here I only need 2. Now if we made 3 spins, we would have 8 different states. I need to give you 8 different numbers to define the state of those 3 spins. Whereas classically it's just 3 bits. If you keep going, what you'll find is that the amount of equivalent classical information contained by n qubits is 2 to the power n classical bits. And of course, the power of exponentials tells you that once you have, let's say, 300 of those qubits, in what we call the fully entangled state. So you must be able to create these really crazy states where there is a superposition of all three unders being one way and another way and another way and so on. Then you have like 2 to the 300 classical bits, which is as many particles as there are in the universe.
How do scientists and engineers design billions of nanoscopic memory cells that can reliably trap electrons for years on end? This is crucial because if the electrons are not properly trapped, your saved pictures and files would become corrupt, and you would lose entire sections of data. To solve this and prevent electrons from leaking out, scientists and engineers surrounded the charge trap with dielectric materials, which are non-conductive insulators that stop electrons from passing through. You can think of this charge trap as a valley, and the insulating dielectric as the walls of the valley. And when electrons are moved onto the charge trap, they become trapped in the valley with no way out, and they can stay there for years on end. This is the basic idea of how your smartphone stores its information. However, this setup poses a new issue. You see, the channel where the electrons come from is over here on the other side of the dielectric barrier in a valley of its own. Now we have two valleys with a rather high barrier in the middle. Electrons can now comfortably stay in one valley or the other. But here's the problem. How do we move the electrons we want from the channel across the dielectric and into the charge trap valley? Or, in other words, how do we write information to a memory cell? Well, that's where quantum mechanics comes into play. In classical mechanics, this electron is a localized point charge with an energy level. The dielectric is an electrical insulator, and the minimum energy level required for electrons to get over the barrier is so high that doing so would take a lot of energy, which would damage the barrier itself. And thus, the electron can't pass over the dielectric. However, in quantum mechanics, the electron's location is not a point, but rather it's a probability density, or a cloud, that depicts where the electron is most likely to be found. When we apply a positive voltage on the gate over here, the positive electric field attracts the negatively charged electron's probability cloud from the channel and pulls it towards the charge trap valley. If the dielectric barrier is thin enough and the pull from the positive voltage on the gate is strong enough, then the electron's probability cloud is pulled far enough across the dielectric barrier so that there becomes a sizable probability that the electron will find itself on the other side of the dielectric barrier and into the charge trap. This phenomenon is called quantum tunneling, since it can be imagined that the electron tunnels through the barrier instead of going over it. And every time you take a picture, your smartphone uses this phenomenon to write information to the charge trap flash memory cells.